Hi everyone, we'll start in 1 minute, I hope. Happy to see everyone again. Hope you enjoy the course. Now, if you have any problems, any questions and so on, please don't hesitate to contact us, me on Evgenia and so on. So it was a pause and now we're ready, almost ready to start to give you material as it is. So let's wait a bit. Okay, today we talk about a very important, in my opinion, topic that's connected to sequential data and to other types of data as well. And it's about how can we deal with embeddings, especially if we are looking at some kind of categorical variables. And this is what we plan for today, to start with like more general overview on what's going on with embeddings, not for sequential data, but for almost all types of data, we need something similar. So we consider them like in a more general setting. Then we'll try to see how it works for sequential data and how can we use specific features of sequential data to make embeddings works better. And so let's start with very basic definition of what categorical features are and how can we encode or embed them. We say that we have a categorical variable if some variable can take values in some set, like of fixed size, for example. I will say that we have like k possible values here, and the feature takes one of these possible values. In this example, as a slide, we have like 7 IDs and 4 different possible values for categorical variable, human, penguin, octopus, or alien. And we can say that the simplest encoding we can provide here is to use label encoding. For each category, we have a specific number, and so the total count of numbers equals to the number of categories from 1 to 4 in this example. And we see that simple correspondence, each human corresponds to 1, each penguin to 2, octopus to 3, alien to 4. And so we have our encoding in a very simple way. We can say it's again encoding because, okay, we have this one-dimensional embedding space and we have like values in this embedding space. They are not dense, they are discrete in this case, but still it's some kind of embeddings. And what is bad about this embedding, if I'm using from the very beginning, then when you have this kind of embeddings, you can rely on any correspondence between points in the embedding space. We can say only about two relations, if they equal or if they don't equal. So we can say that if you have logistic regression and we try to construct something like linear regression model that has this form with this axis are inputs, W is the weights for our G features. Then if you have this weight for this categorical feature based on label encoding, that sounds quite strange because we have no order of these categories. And even if they ordered somehow, we still don't believe that as an increase in the target variable, if we increase x by +1, a specific one, like we replace xi to xi +1, and we change the output by vi because of this product is delta by hat. It sounds quite strange and natural for most type of categories here. So for some approaches, it's okay to have this kind of splitting, for example, gradient boosting and for a random forest and decision trees in general. But we understand this is not like something what we wanted, because this is not like any useful embedding after all. So you can try to use something more complex. Each code, for example, like level encoding based on like binary variables for each of the features. So you can say we have a specific feature related to this type of questions. Is this person a human, a penguin, an octopus? And we say that we have these binary variables, and number of those binary variables equals to k minus 1 when we have k categories in total. Because if we have all values of these features, we can infer, but one, we can infer the value for the last one. So we can say about the alien, okay, if everything else is non-zero, we have non-zero values here, and we say it's 0, 2, 0, 2, 0, 2, 0, 2. If all values here are 0, then we can say, okay, it's 1, so we don't need this particular feature in our case. Now this is like pretty evident if you have only two possible categories, only humans or penguins, only males or females. In this case, we have only one feature. Is this person female or is this person penguin? And so we have this encoding, and this encoding has the form like this. So we have a lot of zeros, some ones. Okay, it's kind of better if we compare this to what we had in the previous slide, because right now logistic regression makes more sense, because we have a weight that is specific for a particular category, and it's kind of better in many cases. We can say, okay, if this person a human, then it's likely have like higher salary than a person who is a penguin or an octopus. For alien can be vice versa, and we have measures this relative difference between different categories by estimating logistic or linear regression in the same way here, and as we have the specific weight for a particular category. Okay, but we see that we still have many problems with this type of encoding. The first one maybe is the distance between two different encodings is similar. If we compute L2 distance between two objects that belong to the same category, we have 0 L2 distance. If they belong to different categories, then this distance equals to 2 because of 1 minus 0 and 0 minus 1 and 0 minus 0 for all other categories. So only two possible answers, only two possible relations. It's not very good, it's not natural if you want to have some meaningful embeddings that say that if two categories are closer to each other, then they should have like closer embeddings. Here it's not the case. We have like equal distances between all categories. Like we can imagine this as like a points on some one-dimensional sphere with distance between each 2 points equal to 2. Okay, does someone have a question here? Anton? Okay, another problem is that this embedding is not dense. It has a lot of zeros and only one non-zero value for each particular object. It means that we need a lot of memory to store these embeddings. It's kind of different from what we had at the previous slide because there was only one feature that corresponds to this categorical variable. But it's kind of serious problem, and we can't say this kind of effective representation because not like low dimension manifold here. It's the points are everywhere. We can specify a region for the points, the embeddings with categorical variable belong to. And this is also better. Maybe we want in the future to develop something that provides more dense embeddings here. But still, it's no problem for some problems, especially if the number of categories is not big. But you can imagine that it's not the case for some types of sequential data. For example, if you're talking about words, and we can say that, okay, word is a categorical variable, and we do some kind of one-hot encoding for words, then have a vector of size 200,000, too large for many applications. Also, you can consider a simpler example when you have merchant category codes for transactions. There are about 1,000 of them, like grocery store or drugstore or ATM. And so, okay, still a lot, but it's significantly smaller, but still it sounds like strange idea to generate 1,000 features from one feature, because typically we want to have not many features in our model. We try to minimize the stuff. Maybe we can do some kind of feature reduction here. And this is like kind of natural idea. If we are talking about embedding of this type, one-hot encoding, we can say that, okay, we have, for example, 10 popular categories. It's like 80% of data have values from this category. And for other like 1,000 categories, we have like remaining 20%. And the distribution is like almost equal here. So they would occupy only a very small part of the sample, the second type of categories. So you can say, let's have 11 features, 10 features that correspond to these popular categories, and the remaining one, that means that this particular object has a category that is different from what we have here in 10 popular categories. So it's just a label that we have is a different one. So we are doing like this. And like in many problems, it's enough to consider something like this. But there are definitely a lot more approaches that tries to have some encoding for categorical variables. Okay, you can look at some benchmark embeddings, for instance, on different types or different methods for categorical features encoding. There is a benchmark of this page. And so what he did, he used a lot of problems and calculate they were all classification problems. So he provides a categorical encoding for features that are categorical and measure the final ROC-AUG score with different types of validations for each ROC-AUG. And then he averages results among all encoders. And so if we can compare average performance scores for each method, and you can see that, okay, I will deep dive into this validation type a bit later, but basically you can see that performance is pretty different. Okay, there is some scaling, so it's not actual 0.5 ROC-AUG values here, but there are some scaling, and from the scaling you can see that the Helmert and some encoder, frequency encoder, are much better if we have non-validation, and we'll later see why this kind of stuff is bad. One, and why we need this single validation that makes almost all approaches kind of are close to each other in terms of performance. But let's consider like typical encoding scheme that's quite popular for Kaglers and for all other The name of this encoding is target encoding. In this case, we say that the approach is the following. Okay, we have like this categorical feature, like 0, 1, 2, 3, 0, 0, 1, 2, 2, 1, 3, and we have value of the target variable. You can imagine this like a regression. So 0.1, 0.2, and so on. And so we want to have some encoding that's meaningful and allow some ordering for the features. So let's select all objects with the same value of this categorical variable and calculate the mean value for it. So we have 0.1, 0.7, 0.3, and 0.5, for example. And we calculate the mean value over all those variables, over all those objects, and so we have 0.4 as the mean value of this stuff. So this is what we are doing for the first category. For the second, we are doing the same. So we have for 0.2, here we have 0.7 and 0.3, 4, okay, 0.3, I don't like it, 0.9 for each variable. And we can see that we sum all the variables, divide by the number of objects, and get 0.6 as an encoding for each variable. So basically it equals to the values of the target for this category, where A is all objects such as some categorical variable have the value like K. This would be our encoding K value. And so with this, what we replace, how we replace this labels of encoders with some meaningful values. We try to construct some correspondence between the target variable and the variable and categorical variable we work with to have something meaningful. It's kind of works. It's kind of was popular and still popular for many Kaggle competitions. But okay, can you name what's the problem with this type of encoding? Can you like make a guess? Any ideas?
Maybe we have a B-model distribution for a feature and it can't work.
So, can you elaborate more? What's bad about the model distribution? Because okay, we have a lot. We have some values here. They are not even distributed. We can have some dense, some not dense variables for this categorical feature. Andrei?
Yeah, I think maybe my idea is that you have, for example, your feature has a distribution of mixture of two normals with different means, and if they are far, and if distance between means of this distribution is far, you just your mean value that don't represent anything.
Are you talking about the target variable? Yeah, so you have for this Gaussian distribution. Okay, I hope so. Yes, this can be a problem, and maybe something not meaningful. And in this case, it will be equivalent to just having this label encoder that I presented in the second slide. But there is a more general problem. that we need to be very careful about construction model on the basis of encodings, because we have this kind of data leak. If we use the same sample to generate the value for each encoding and the same sample to construct the model, then we have this bias towards these features, because these features are like have some maybe quite strong correlations with the target variable. So there is like an intention by a machine learning model to overuse this model. And in this case, we observe typical overfitting, because these features look stronger than they actually are. So you should be careful about how you construct the model. And typically, you construct this encoder, target encoder for example, true false. Then you construct the model using the third fault because and you don't use the third fault to generate the values to this encoding. And in this case, it's a correct way to think about this encoder because you have like no bias introduced here, because they doesn't lead to this third fault. And so this is the basic approach. So you like get encoder for fault 1, then you construct and 2, then you construct model using fault 3 here, and you use encoder you constructed earlier to get the features, to get this preprocessing done. And then you can test your model for fault 4. So in this case, we have 2 steps. Like the first step is to encode categorical features using like target encoding, or maybe select as encoder. And the second step is to apply the model. And so in this case, it's more or less correct way to get the result. This is called single validation, as far as I can remember. And so it's okay. And also you should be careful about how to you get this model to production then. So I described some approach to test the model, but definitely we are also interested in how to use this model for inference. And for inference, you are doing something like this. Okay, you need to get these categorical features for like the whole sample, and you know that it's prohibitive to use a simple approach, because if you use a simple approach, then you will get overfitting. So typically what we are doing is to have this double validation and to have another split of points inside this validation. Okay, this is the strategy. So basically what you are doing, you say that, okay, you have some faults, let's split it to sub faults and get this encoding for the last fault. So you have these faults that are taken out of our training sample and then included back. In this case, it's okay, and we have this particular encoder for each part of the data. And as we have a lot of parts, they're quite diverse, and we hope that they represent well the distribution of the target for our training sample. And so we have this new feature, and for this new feature we can use to construct a model using all the data, because we never use the same data to construct the encoder and to construct the machine learning model. And we can transfer this to our test sample to make everything work fine, and we hope without overfitting. This is what we call additional validation when we are thinking about target encoders. Okay, is it clear? Please write plus sign if it's clear. Now, Okay, good. And so let's think more. So let's go back here. And so we can see that if you have non-validation, that for some approaches, the final result is quite poor because of this overfitting issues. If you have this additional validation, additional step in model construction, we have significantly better result for all of the methods. And these three encoders are no longer in top. I will not go into much more details here. Let's mention like we have target encoder here, specific cat boost encoder, and so on. So please take a look if you're interested. They're pretty simple, so there's just like simple formulas. Nothing very serious, but it's interesting to think about it like this. Another approach to think and to construct an encoding is for sure based on neural networks. As the categorical encodings, again, we can say that we want for each feature, for each value of categorical feature to have a set of numbers here, two-dimensional or maybe three-dimensional, and so on. And so we can construct an end-to-end approach to get this neural network work here. And we can optimize this encoding to make the result better. If we can construct fully connected neural networks that have part of the features from this categorical variable and two other features like common continuous features, then we run backpropagation and we try to optimize the encoding vector for each category. Like this called encoder layer, I suppose, in PyTorch. And it can be used to make the whole thing better. So we use direct optimization of like encoding for each categorical feature. And in this case, we finally are closer to our goal. We paid less attention with other encoders to our goal to have meaningful representations. We rather tried to make the model work better, but here we are one step closer to this approach. We say that right now, if these encodings are closer, maybe it does mean that they have something in common. These two categories are good, for example. Okay. Humans and penguins are closer than humans and aliens, and penguins and octopus are closer to each other than to other species we mentioned on this slide. So in this case, also we see that our approach is an end-to-end one. So I've used like one general pipeline to construct these encodings. So this is pretty much what we do and what we achieve. It's not the best approach, however, in many cases it works not very good when we are talking about tabular data. But okay, still an interesting idea. And if you can construct a good overall fully connected neural network, maybe it can work too good. So this was the tale about how can we create categorical encoders for tabular data. Let's now try to move to sequential data and see what differences do we have. Again, we can apply the same ideas and we can try to use this one-hot encoder. So we have, for example, for a dictionary of words, encoder that has one as a feature, as a place that corresponds to this particular word. In this case, we have, again, sparse representation, not very useful, and so on. And even if we use bag of words model and like calculate the number of occurrences of each word in the sentence, we have kind of strange representation. Again, very sparse, a bit denser here, and this is kind of bad. And we can try to improve on this, for example, using TF-IDF. Let's make a few comments on this. So we suppose that we have some terms, tokens, and some documents. And for each document, for each description, we can calculate number of occurrences of tokens or terms or words. This document that we labeled as empty. Also, we have the total number of documents, and we have number of documents that include this particular token. Okay, we can say that if the token is too common, then like it's adds a little. If you have some words like in, a, or there, they typically in almost all documents. Doesn't make much sense to include it. But if you have some token that is quite common in the document, but is not very common overall, then we have this term frequency term here. Also, we can have inverse document frequency. When we calculate total number of documents and number of documents that has this token G, and we take a logarithm. And we can say that we are interested in this TF-IDF feature. That's a product of term frequency and document frequency. And so we can say that how often this term happens in the particular document, and we try to normalize it by this IDF term. Why we take the logarithm? I think we have some linguistics explanation how it works. But more general, it's another heuristic here. For term frequency, we have very similar to count encoder. We just calculate the number of occurrences of this word and normalize by the total word count in the document. And these TF-IDFs can work well. It makes RAID tokens more important and common tokens not that important in our decision, like smaller magnitudes. And if we have a logistic regression, probably it matters. We have like meaningful features. And maybe for neural networks, it also works. But for decision trees, it doesn't make much difference what kind of encoding we use. Usual categorical encoder or this more advanced TF-IDF encoder for categorical features with the large number of categories. But still, we have this sparse representations a problem. Maybe it would be more interesting to have embeddings of objects. And okay, we have had this embedding from like training of convolutional neural networks, for example. But for sure, we can try to do better and try to focus on our particular task on how can we deal with this problem for categorical encoders. So basic idea is to learn embeddings of the objects. It's similar to what we did with this neural network encoders for categorical features for tabular data. We can say that for each token, for each categorical object, we have this embedding, this dense one. Then we, for example, input to our RNN here. So you say that we have this initial words, 1, 2, 3, 4 tokens. We have embeddings for each token. So we have the same token at different places. We will have the same embedding of it. And then we add one more layer, for example, RNN layer here is connected to each other. These blocks is RNN. And in that we have encoding of a sequence that proceeds all encodings during the work. Also, we can try to use backpropagation and optimize these encoders by trying to minimize the loss function, means the correspondence of our output and the true value. And it works quite fine. And in many cases, we get kind of useful models here kind of useful embeddings. They are dense by construction, so we don't limit it and don't care too much about particular cases. And so on. And so this one way, and doesn't use like any structure of the data, and uses the power of neural networks. And if we have a really large neural networks, recurrent neural networks, and really large data samples, it works like a charm, and we have very good results in the end. We can try to look at these embeddings and spot some interesting things. I think almost all of you have heard about something like this. For example, we can try to build and observe some relation between words. For example, the difference between the embedding of a woman and embedding of a man is kind of similar between the embedding of an aunt and of an uncle. And so similar things occur between king and queen. So we kind of learn semantic responses between different objects. And the same way we can try to go from singular to plural words. So we add some vector to our embedding, and we get this plural words here. Okay, it's kind of related to the generalist entanglement, and it's kind of surprising that we have kind of things, this kind of thing automatic. So this embedding, meaningful embedding directions, especially if you think about like the more or less general approach. But sometimes you observe this behavior. Sometimes, unfortunately, not universal rule that for each learned embeddings, we would see something like this huge deep diver and see if it holds or not for a particular thing. Also, okay, these relations are not very useful, in my opinion. You can say something very common about this stuff here. And okay, I think right now it's time to turn on your cameras and to make this attendance photo for all of you. Okay, I'm waiting for you to be here. Okay, I think that Evgeny, Polina, Antoinette, Eduard doesn't want. Oh, okay, Eduard here too. True. Okay, good. Okay, thank you a lot. And in a moment, we'll be back to the lecture. Okay, so let's go back. I think you can now again see the slide here. And to this slide, we again see this useful embeddings. Okay, we can try to use different heuristics to generate embeddings. And maybe one of the most popular embeddings before word-to-vec is before neural networks and this kind of training is word-to-vec. In this case, we can say that we have this conditional likelihood of words given another word. So say, okay, we have this J in some time window, j does not equal to 0, like in neighborhood, a window size of this kind of stuff. From t minus c to t plus c. And we run this kind of approach for all other dots. So we start like from 0 is the center of this window to t as the center of this window. And we want these conditional probabilities to be high. So we kind of maximize the probability of co-occurrence of relevant words that we learn from data. Okay, to make this work, we need to define this term. And for this term, we can define it, for example, like this, if we have embeddings of our words. So for example, we can say that we have this embedding for this input word and another embedding for output word. And in this case, we have this cosine similarity or scalar product to have the correspondence between them. And also we normalize this probability by dividing by the sum of all the words, of all possible words in our dictionary. So it works like this here. And we have a particular probability for this word and so on. So now we have everything defined. We have this probability we want to maximize, and we have some parameters to maximize because we observe a lot of texts and a lot of words in these texts. So we run this procedure. We can take easily all the derivatives, and we get in the end embeddings for all words that are based on co-occurrence of the different words. It's kind of self-supervised approach. You don't need any labels as what we did for recurrent neural networks or the types of networks, and we learn embeddings. Instead, we just look at unsupervised texts and learn quite useful embeddings, and they can be used in many cases. Not that there are some papers on how can we improve this, and we need this improvement because kind of hard to calculate all the stuff. We can instead try to replace the complexity of the initial procedure of the size of the dictionary W with odd log W if we construct a proper way to deal with calculation of these conditional probabilities. And also, if you look at this kind of stuff, we see that we have really some particular features of objects identified by word. There's some example from here on what kind of saliency maps or values of embeddings you have now. And for example, here we have something common here and something not common. Okay, if we have all this are feminine, so maybe this feature corresponds to that. This like female gender for all these words. Okay, we have boy here. I'm sorry. Maybe it's not that stuff. Also, you can see that this water have different features here, and all other objects that are like different kinds of men have different representations. So, and also we have, for example, here two different words for queen and king, and this feature is different from all other stuff. Maybe it's kind of a royalty specific feature. Okay, so that's all for me for today, I suppose. Yes. And maybe I can finish what I missed during the previous lecture on how can we deal with different architectures, because I think it would something really was very fast to complete in the end. Yeah, so let's start in 1 minute. So again, we go back to previous lecture and we try to construct a nicer block for our RNN model. And we see what we can do and what we can do. And we can test this kind of stuff in different ways. Okay, I'm sorry. Okay, and so we can say that we have performance for one data set and for another data set, and we can say that there are kind of correspondences between the quality of different architectures. We can say, okay, this is something like this, and also we have some architectures, again, that are better than default RNN, LSTM, and GRU. Also, we can say that we have some similar observations for age and accuracy and RMSEF for different data sets. So we kind of say that like generally better blocks and generally worse block that tries to capture longer dependencies. We can try to run another experiment and try to predict the performance of some RNN blocks. So we kind of generate about 11,000 of graph-to-vec features and try to construct the model that predicts like the score of an architecture for these features. And we can use neural network or gradient boosting to predict the performance. And if we have a large enough sample, we can try to predict the performance of a block with high probability, with this being kind of close to 1, 0.8, I suppose, a good correspondence, because there are some noise here and so on. Also, we say that we can use this kind of thing. Okay, again, this scatter plot for a good model for a gradient boosting regressive and for dense neural networks here, and we have some correspondence between these two features. And so we can say that we kind of can predict the performance of architecture, but again, it's very hard to construct something better, more advanced than classic GRU or LSTM block. They're kind of good, especially if you're looking in NLP domain. In other domains, it sometimes makes sense, but also it makes, in many cases, even more sense. Try to optimize the hyperparameters and carefully construct your process of training to avoid like gradient vanishing or gradients exploding, and having a stable training allow you to construct better models. I think it's all from me for today. Thank you for listening. Rodrigo will continue with the seminar in half an hour. So please have a little break. Maybe you will come up with some questions, and then you will see the seminar a bit later. Thank you for your attention and have a nice day.